In today's class, we are going to cover a very important theorem named Cook's theorem, and it is based on the Boolean satisfaction problem, whatever we have learned in the previous class. So let us begin what we are going to do today. Just see, today we are going to prove the NP completeness of the SAT problem. SAT problem means the satisfiability problem that we have visited in our previous lecture, right? Now here, how to prove that Cook's theorem means Cook's theorem is going to prove the fact that SAT is NP complete. Now what will be the benefit of proving it? If we can prove any problem, any standard problem to be a NP complete problem, then that mapping part, that is polynomial time reduction part, will be very easier. So if this is a base problem, for other problems where we are not, means we will not directly try to prove those problems as NP complete, rather we would try to map those problem instances with the problem instances of the SAT problem, so that we can prove that the new problem is also a NP complete problem. Okay, so let us see what Cook's theorem is stating. It is stating this, that SAT is NP complete, right? Now how to prove it? Here you know that the first part is what if we have to prove any problem to be NP complete, that first we have to prove that okay, my this problem is NP, right? Means it can be implemented using a non-deterministic Turing machine, and that can to execute the whole function in polynomialic amount of time, right? Now the first part of the proof is showing that SAT is in NP, and this part is quite easier, but we will see the later part that will be a little bit hard, but first let us focus on the first part. Here we use a non-deterministic ability of a non-deterministic Turing machine to guess a truth assignment T for the given expression E, right? So we will see that for a given expression E, it can have any number of variables, right? So we have to go for those truth assignments for which this expression or Boolean expression is satisfying itself, right? Means those truth value we are going to find out for which the truth value is true. Okay, so if the encoded E is of length n, then order of n times suffice on a multi-step Turing non-deterministic Turing machine. Why is it so? Because we have seen earlier that if we incorporate a non-deterministic Turing machine, and that too is a multi-step, so we can parallelize the whole process, right? So whenever one branch is checking for its all the choices, the other branch is checking for all the choices. So in this manner it can be done, the total encoding can be done on length n, and that too can be completed in order of n time, right? And this non-deterministic Turing machine has many choices of move and may have as many as 2 to the power n different IDs reached at the end of the guessing process, where each branch represents a guess to a different truth assignment. So this number of choices it will have, because for any non-deterministic approach, whenever the length of the string is n, so there can have 2 to the power n number of choices, right? Now we have to evaluate E for the truth assignment T, that is if E of T is equals to 1, then only we are going to accept, otherwise we are going to reject. So you can see this part is quite like deterministic approach. For 1 output we are going to accept, and for 0 output we are not going to accept. So this is a kind of deterministic approach, right? Now this evaluation can be done in order of n square time on a multi-step Turing machine. Why is it so? Because we have found that for each path it is consuming n order of n times. So for n number of paths, if there are n number of paths, there will be order of n square amount of time consumption if we use a multi-step Turing machine, non-deterministic approach obviously. But if we have to simulate the same thing using a single tip Turing machine, means the working whatever the multi-tip Turing machine is doing, that would become square of the whatever my multi-tip Turing machine is consuming, that is nothing but order of n to the power 4. But now you can see whatever the approach is, we have already seen it in our previous lecture. Still we have to recapitulate, because the Cook's theorem, for proving Cook's theorem we have to do the whole thing, right? We have to prove both the properties, right? So this is the first property. So you can see the total entire thing can be done in polynomial amount of time. So if we use a non-deterministic Turing machine approach, the problem can be solved in polynomial amount of time. So we can say this is a NP, right? So this is a NP. Till now it is okay, but to prove NP complete we have to prove one more property, right? Now we must prove the hard part, that is L is any language in NP, then there is a polynomial time reduction of L to SAT, right? So this is the harder part. So if you remember the definition of NP complete, what we learned in the previous class was like, first point was a language L to be an NP complete, it should satisfy L should be in NP, means it should, this L, whatever the language we are feeding to the Turing machine, that can be solved by a non-deterministic Turing machine in a polynomial amount of time. And the second part was, this L is any language in LP, then there is a polynomial time reduction of L to satisfiability problem, right? So this part is, we have to find out that how this can be reduced to polynomial time reduction, means what is the actual mapping. So if we can prove the two properties, first property has been proven, if we can prove the second property, then we can say that my SAT, that is satisfiability problem, is NP complete, right? So we may assume that there is some single tip non-deterministic Turing machine M and a polynomial P of n such that M takes no more than P of n steps on an input of length n along any branch. Okay, for now we are assuming this one for some single tip non-deterministic Turing machine, and a polynomial, we are assuming it to be P of n, and we will say that across any branch it will not consume more than P of n. Why we are assuming so? If the length is of n, so each branch of Turing machine is going to consume how many number of, maximum how many number of inputs it can be fed to, that is n only, right? It cannot be more than n. So each branch can take maximum of Pn, means whatever the polynomial is, but it should not be more than that, right? Now further we have proved for deterministic Turing machine that it can be proved in the same way of non-deterministic Turing machine. This is the other part, we have already done it, right? Now we will assume that M never writes a blank and never moves its head left to the initial head position. So why we are assuming this one, or rather why this is the definite statement? If you can see, if we have to process a n-length string, if my head or the finite control starts at the initial unit, it can move up to n place, right? So there is no meaning of moving left to the initial position or right to the initial position, because it consists of only the blank symbols, right? So no, if we can just cover all the n length, that is okay for us. So we are not going to cover the blank positions, right? Now if M accepts an input W and the length of W is n, then how is it going to do? If we have to state the moves of the Turing machine M more formally, we have seen this kind of representation in several number of times. You can see here alpha naught is the initial ID of M with input W. If you remember what an ID of Turing machine is, it is nothing but a combination of an input symbol, a state and a string, and rather a tape symbol, sequence of tape symbols may be there, and it would move to a new state and write something to the place of the original tape symbol, and the direction is mentioned there, whether next it is going to traverse leftwards or the rightwards, right? Now if this is the fashion of representing the ID of any Turing machine, so we are assuming alpha naught to be the initial ID of M, and it is having an input W because we are processing the string, input string named W. Now this much of sequence, if we assume the different IDs like alpha naught, alpha 1, alpha k, and then k should be lesser equals to p of n, because we are restricting ourselves to traverse up to maximum n length. We are not going to go beyond that. So the k should be, means the ID should maximum reach up to pn, means whatever the polynomial n is holding, means whatever the length of the string is there, up to that part it maximum can move up to that part, right? Now alpha k is an ID with an accepting state. Now we would assume alpha k is an ID with accepting state. That means if it can traverse up to k number of number of IDs, if it can traverse, then it can move to the accepted state. Do not think that k is always present or accepting state is always present at the end. Here we are depicting k to be lesser or equals to pn, so it can be anywhere in the sequence of IDs. It can be at the beginning part, it can be at the middle part, it can be at the end, anywhere, okay, but that should to be within the total length n, right? Now each alpha I consists of non-blanks only, except if alpha I ends in a state and a blank and extends from the initial head position the leftmost input symbol to the right. So here you can see that since we are considering the total input part, so there cannot be in any blank symbols present in between. Only thing is that if we have reached the end and after that say we are showing any transition for the last state, so whenever we will show the transition, so after that the tape symbols we need to encounter may be blank. For other cases there will be no blank symbols, okay. So if we have to summarize our strategy which we are going to follow, it would be like each alpha I can be written as a sequence of symbols xi0, xi1 followed by x, okay, that I should be in suffix I comma pn. That means that here alpha I can be sequence of this kind of thing. So you are quite sure that how to write an ID. So out of whatever the sequence of symbols we are using, out of all the sequence or all the symbols present in this sequence, only one of this is a state and the other must be tape symbols, because at the same time for any ID at a particular time a Turing machine cannot point to more than one number of states. So when you have seen that whenever we had to represent it using a multi-tape, if you remember that whenever we were showing the transition, so based on the whether the direction was right or the direction was left, my state, means a new state where it is transiting to was being placed after a tape symbol or before a tape symbol, okay. So tape symbols were there and only one state symbol was there. So this representation on the sequence of symbols should follow the same pattern only, okay. So as always we assume that the states and the tape symbols are disjoint, so we can tell which xig is state and therefore tell where the tape head is. Here for the generalized purpose we are just using x symbols for all, but if we have to really implement this one, then we would denote my state with q and input symbols with any other variables, and most of the cases we may use x, right? So we can since we can find out which of the x, means whether xi0 or xi1 or xi2 or x whatever is, whichever is the my state and rest will be the tape symbols, then we can find out, okay, my Turing machine is processing this state now. So it can be find out easily from the total sequence of symbols. Note that there is no reason to represent symbols to the right of the first pn symbols on the tape, because they cannot influence a move of m if m is guaranteed to halt after pn moves or less. Means here we are restricting our working of the Turing machine up to n symbols. So definitely after processing n number of symbols it will halt. So we will design in that fashion only. So it is not going to process any input after the nth occurrence. So we are going to restrict it up there, okay. Now to describe the sequence of IDs in terms of Boolean variables, we create a variable namely y suffix ija. here we are representing, right, you know, that this total to be to represent the total thing using a Boolean variable. So we are representing in this fashion yij a to represent the proposition, right. So xij equals to a means here a will represent the state. If you consider the, or if you consult the previous slide again, there we have taken xij as a state and rest symbols in the sequence was treated as our tape symbol, right. So here if a is the state and then yij will represent my tape symbol, right. So if we have to go with the Boolean variable, it may be I may be 0, j may be 0, the next counter I may be 0, j may be 1. So in this fashion we can move, and for a is a state in which my Turing machine is pointing to, right. Now we express the condition that the sequence of IDs represents the acceptance of an input W by writing a Boolean expression that is satisfiable if and only if M accepts W by a sequence of at most Pn moves. So if we have to represent using the Boolean expression, it should be satisfiable means the value should come to 1. That means we should follow such a path, or that path we are going to accept for maximum of Pn moves. That means what? Here 1 means what? True. That means the result satisfiability means we are going to pick up those values whose resultant is 1, right. So true means what? Ultimately following any number of moves that should be restricted to maximum of n moves, following that path we have reached to my accepted state. So if we can go to an acceptance, or rather it may be going to final state, or it may be halting. So at the end of the day we can say that okay, this we have got a result. That means what? We have to move, somehow we have to move to such a state which is an acceptance state, right. So that path we have to follow, and if we can follow that n number of moves, and definitely if the path followed is correct, my Boolean variable, whatever the expression we are writing, that is going to give an output of 1, right. Now the satisfying statement will be the one that tells the truth about the IDs, that is y of ij will be true if and only if x of ij equals to a. That means what? If we consider any tape symbol, or rather any states to be xij, which we are going to represent it by a, if we follow the correct path, then we have to pick up the correct state symbols as well. We cannot move to different other states where the movement should not be there. So definitely here xij should be a, and if we take a as any other value than xij, since here we are considering xij to be my state symbol, that's why it can be true if we follow the correct state only, otherwise it will not be true. Okay, now to make sure that the polynomial time reduction of L of M is to SAT is correct, so what we can do, we will carry on the computation in three different following three different ways, or three different important things. That is, first is starts right, the next is next move is right, and finishes right. Right, start right means the initial ID is q naught w followed by blank, right. Starts right means, just see here, if we can start with the start symbol, and if we can move along the path where we are ultimately what? Satisfying all the symbols that are present in w, and after the end of w there are blanks, that means we are starting correctly, right. Now next move is right means we are moving, we will always move to the right side. We are not going to, if we start from the initial state, we will not move definitely to the left, because left symbols are totally blank, there are no symbols we have to process there, so we have to move right. So each subsequent ID follows from one previous one of the possible legal moves of M. So the next move means from the starting, if we start from the initial state, that is q naught, next move will be a correct move if we consider any legal move of M and can keep on following the legal moves of M, right. So the next move should be the legal move that a Turing machine is allowing us. and finishes right will be there are some ID that is in accepting state. So if we can finish our processing at such a state which is the accepting state, then my total working will be okay. So we have to start correctly. That means we have to start with initial state and the total W, that is the string which we are going to process. Then we have to take a move which is a legal move defined by Turing machine, and we have to finish in such a ID where the state, the ID where we have finished, the state associated to that ID should be an accepting state. Okay. Now there are few details that must be introduced before we can make the construction for Boolean expression precisely. So let us see what are the few details we have to learn before we can move directly to the theorem. First, we have specified IDs to end when infinite tail of blanks begin, right? So when we are going to end, because after the end of total string, after the end of total div symbols which we have to process, when we encounter infinite amount of blank symbols, that means we have entered the last processing div symbol, right? So there we have to specify the ID to get end. Means whenever my ID is going to get a blank symbol after its first processing and other blank symbols are carrying on after that, total blanks are present, then it has to we have to specify that ID to be a finishing ID. After that we will not move anymore, right? It is more convenient when simulating a polynomial time computation to think of all IDs having the same length, Pn plus 1. Why Pn plus 1? Because after Pn moves we will reach the end, and if we have to check whether we are encountering a blank next, we have to encounter one more move. Okay, so that's why to identify a ID to be a end ID, we have to incorporate one more move. And the second thing what we have to consider is, it is convenient to assume that all computations continue for exactly Pn moves and therefore have Pn plus 1 IDs. Why? Because if we complete Pn moves, my ending ID will be a one more ID which is encountering blank after it. That's why there will be Pn plus 1 IDs. Now even if acceptance occur earlier, but if acceptance occur earlier, there may be some cases where acceptance may occur earlier, but we cannot generalize in this case that acceptance will occur earlier. So for this purpose, if we have to generalize all the thing, we have to consider the total computations will end, or total number of branches that it will follow will be of Pn moves, means maximum Pn moves can be there. So we have to consider the maximized case right here. So we allow each ID with an accepting state to be its own successor. Now since we are defining all computations will have exactly Pn moves, now if we have to write an ID for an accepting state, right? So in that case we also have to keep a successor of the accepting state also, because if we can incorporate a move like alpha can transit to alpha, that means alpha, that is the ID for the accepting state, is transiting to itself, then we can apply this generalized technique to all, right? There may be maximum, say from alpha naught to alpha n, means that is the accepting state. If we have to follow maximum of Pn moves, say for alpha 2 we have to follow maximum of n number n minus 1 number of moves in whatever the fashion is, and if at the accepted state we are incorporating a transition to itself only, then it can be done in one move only, but still we can generalize the concept. Maximum number of moves can be n, so everything will be covered under this generalized concept. Okay, so we can assume that if there is an accepting computation, then alpha of Pn will have an accepting ID, and that is all we have to check for condition finishes right. That means finishes right means ultimately after n number of moves we have come to maximum in number of moves. It can occur earlier as well. We have come to such an ID where an accepted state is there, so we have finished right. Now let us see a figure what it is suggesting. You can see here one block is having IDs, right? So here if you focus on the column, it is showing different IDs present, and in the row wise just how many moves we have to compute, right? So here polynomial time computation will look like this. If we have to just refer this chart all the time whenever we will be into the proof, right? Now here the rows correspond to the sequence of IDs and the columns the cells of the tape that can be used in for computation. Okay, now see here how many number of squares can be there. You can see here it is starting from 0 and ending at Pn. Okay, so it will be Pn plus 1 whole square, right? So it can move row wise, it can move column wise, that's why the square part is coming. Now the number of variables that represent each square is finite, and it depends on the on m only. It is the sum of the number of states and the tape symbols of m. That means if we consider the first cell element, that is x00, it should be a finite. Okay, why finite? Because it will consist of a state and finite number of tape symbols. That's why the total will be a finite one. Now we will now give an algorithm to construct m and w, a Boolean expression like EMW. Okay, so we know that EMW, E stands for expression and M will be my machine based on which we can generate the Boolean expression, as we have learned so far. Now the overall form of EMW is of U and S and N and F. Now here we will find out each separately. We will find out U, we will find out S, we will find out N, and we will find out F. And here S and F are the expression that says M starts, means for S we will see how to start, means how M is starting correct or not, and then N means moves, whether it is moving correct or not. If you follow the previous few slides, there we have incorporated 3 points. There we have to assure that we are starting correctly, we are moving next correctly, and we are finishing correctly. So that 3 part will come under S, N and F. And U is a universal or unique symbol for each cell. So each cell should have the unique symbol, because each cell will have one state and a tape symbol associated to it, and that should be unique. Means whenever we are associating my first alpha naught with 0, so whatever the combination of one state and tape symbols are, if we go for the next, it will definitely going to change. So that should be unique. So let us define the unique first. It is saying that it's logical AND of all the terms of the form y of ij alpha and y of ij beta. What is y of ij alpha? Say ij stands for the value, that is, it may be either 0 or 1, and alpha means the state associated with it, and beta is another state. So since we have means yij alpha means the content of one cell, and yij beta means the content of the other cell, and that too should not be same, and definitely alpha and beta are not equal, right? Alpha and beta are what? Two different states, right? So if we have to represent it using a Boolean variables, so it should be like not of alpha yij alpha and yij beta, because both should be different all the time, right? That's why this is a unique definition. That means we are assuming that this content of each cell and should be unique, right? It should not be same, and this total number of terms will be definitely order of p square n. Why is it so? Because I have already shown you in the previous slide that the maximum number of cells present in the total table should be Pn plus 1 whole square. So if we have to find the complexity of it, 1 is a constant term, so we can easily discard it. So it would be like order of p square n, means it will be the total number of cells present and square, because we are considering the both the way row wise and column wise as well. So what starts right is saying now, so if you just follow the table, as a reference, but I have not kept a table in all the slides because it would consume more space. That's why just remember the table for now. Now x00 must be the start state q0 of m, and x01 through x0 alpha must be w, means x, if we start from the x00, it is a start state q0 of m, and we have to move through x01, then ultimately at the end, if we reach at the end, that means we have covered the total length of string, that is w, and the remaining xij, that means after p and n number of moves, all will be blank. Okay, so start right means we have started right if either means of if we follow this total path correctly, that means we have to incorporate ending here, means all should be in its correct position. Okay, so what should be it? X first id will be, if you follow the total chart, it starts with 0. X00 is my starting cell value, so it would be y00 q0, then y01 next move is id is alpha 1, then 2, and in this fashion it would cover up to pn, and you can see one blank is after that, because after n number of moves there is a blank symbol encountered. So this should be the start right criteria. If we can follow this one, then we have started correctly, and this encoding we can do it in order of p n time on a second tape. If we consider a multi-tape, so this total has maximum of length n, so it can be computed in order of pn. Now we have to consider this one, then finishes right, because next move is correct is a little more tricky, so we'll cover that later on. Let us first focus on this finishes right. So since we assume that an accepting id repeats forever, acceptance of m is same as finding an accepting state in alpha of pn. Remember that we assume m is an NTM, and that is if it accepts does so within pn steps, thus f is the OR of the expression fj. That means what? If alpha pn is any acceptance state, right? So whatever the move means, whatever the finish means, for any combination of alpha of pn, if we can reach any one of those IDs, or if we can pick up any one of those IDs which is containing alpha of pn, then my finish right will work correctly. So what will be the expression? It will be y of pn j alpha 1 for if it satisfies for alpha 1, okay, if it satisfies for alpha 2, it is also okay, if it satisfies for alpha k, it is also okay, because everywhere my acceptance states are there. So if any one of this we can finish in any one of this id, then my job will be done. Similarly, the same thing can be done in order of pn time. Now let us focus this complicated one. This next move is right. So next move is right means we are assuming that whatever move we are taking from a particular ID, what is the next move we are considering it to be correct. So how we are going to consider that to be correct, right? Now here you can see, if you just follow the table, you can see one, that if we consider this ID x of I plus 1 followed by j, right? So it is depending on what? If you just consider the total table, either at this position x I plus 1 j, it can reach this position from its left symbol or else from its right symbol, right? So it will depend on x I j minus 1 or and x I j and x I j plus 1, right? So it can come from these three symbols only. Now if one of the symbol is the state alpha I, then the particular choice of move by NTM m, right? So if this any of the state is alpha I, that means if any of these symbols is having a state of alpha I, that means if any of the symbols is having a acceptance state with it, then the move will be right. Now here we will consider two conditions. One will come under A of ij, another will come under B of ij, and we will see that if any one of them satisfies, then the next move will correct. Now aij is saying that the state alpha I is at position j, that is xij is the state, right? So if xij is the state, that means my state alpha I is at position j, that's why xij is a state, right? And there is a choice of move of m where xij is the state and xij plus 1 is the symbol scanned, such that this move transforms the sequence of symbols. If this is the situation, then see what can be the move. If my previous symbols are like this, xij minus 1, xij and xij plus 1, it would move to what? It will move one more unit, that is I will be incremented by 1. That's why xi plus 1, j minus 1 and the rest, right? So here we are considering that my xij is a state and my acceptance state is there, that is alpha I, right? Now if xij is an accepting state, there is a choice of making no move at all. So if we just see whatever we have seen the transition, if xij is the acceptance state only, so movement may not be required because we have reached our goal. Now if the choice is somewhat different, now the state alpha I is not at position j. If alpha I, that means my acceptance state is not at position j. We have considered that if my acceptance state is at position j, so we have covered that part. And if the situation occurs or situation has gone to in a different path, that is the state of alpha I is not at position j, then xij is not a state, and if the state of alpha I is not adjacent to the position, that is if this situation occurs, in the previous case we have considered alpha I as is occurring at position j, and here we are considering alpha I is not at position j, and again whatever the positions are adjacent to xij, right, that is xij minus 1 and xij plus 1, these two are not state either, then what will happen? Xi plus 1j will be equal to xij, okay, because these two are the xij is not at itself a state, and again its adjacents are not also a state, so that these two should be equal, right? Because a state should be there. If this situation occurs, that means these two are equal. Now when the state is adjacent to the position j, then the correctness of position j will be taken care of ai j minus 1 or ai j plus 1, which we have covered in the previous slide. Now if the b condition is holding correct, so then what we can do, how to represent it? Now bij is easier to write. Let q1 to qm be the states of m and z1 z2 be the tape symbols. Now if we consider the previous one, that is y of I j minus 1 2 for all the states and y of I j plus 1, that means we are considering two adjacent locations of xij. So one is one will cover all the choices or all the IDs with the index value I comma j minus 1, and the other will cover with I j plus 1. So this should be or with one another, and for xij, since the xij has not been considered as a state, so we are just putting the tape symbols with it, that is z1 z2 for all the for all the ij combinations. We have incorporated the tape symbols one with the other, okay. And for the fourth line we have kept that either xij will be paired up with z1 and xi plus 1j will be paired up with z1. Why is it so? We are describing in the next slide. Fine. So here if you consider the first two lines of bij, it guaranteed that bij is true whenever the state alpha I is adjacent to position j. Okay, so if you follow that one, you can see that there were or in between the all set of symbols. So bij would either be true for means keeping xij in between, we have incorporated two more lines. One stand for ij minus 1, another for ij plus 1. So if either of the two holds, then it will work fine. So if in that case, if alpha I is adjacent to position j, that means if my acceptance state is adjacent to position j, then either it will be at the location j minus 1 or j plus 1. So for either first line or second line will be true, right? So it will be true ultimately. And the first three lines together guarantee that if the state of alpha I is at position j, then bij is false, and the truth for ni solely depends on aij being true. Now here, if you remember, we have considered for a's expression there xij was a state, and that too had an acceptance id, that is alpha of I. So if this holds, so a will occur, means aij will work and bij will be false, because in this case if my acceptance state is at xij, then definitely it is not going to be present at its adjacent location, that is ij minus 1 and ij plus 1. So it will hold false, and then a will work, b will not work, right? And when the state is at least two positions away from the position j, the last two lines assure that the symbol must not change, right? So now you can find out in the previous slide that what was the last statement saying. It was y I j z1 and y I plus 1 j z1. That means what? If my state is acceptance state is neither xij nor its adjacent location, that is not xij, not xij minus 1, not xij plus 1. So if this is the situation, then there will be at least two position gap to reach the acceptance state. So the final line will do what? For xij, it is keeping it as same. See, here xij will be equivalent to xi plus 1 comma j, because it is not holding correct for any of the three conditions. Not xij is consisting of any acceptance id, neither its leftmost neighbor, neither its means right side neighbor, right? So it will continue as it is. That's why you can see the jet symbol, the tape symbols are written correct. Now we will consider here two important cases may occur. Here either j equals to 0 or j equals to p, and that means the head never moves to the left of its initial position, and we know it will not have time to get more than pn cells to the right of where it started. That means for the first case we are at the beginning only, right? But in the second case we have reached or we have covered all the n cells, and after that the blanks are there, so we will not go at that part. So we may eliminate bi0 and bi in pn terms, because for the first case bi0 will be, we can means minimize the total factor, but still these are the special cases. We will not focus on this kind of thing. We will move with the generalized factor. So in the special case, if j is equals to 0, just go to the original expression of b, just substitute j with 0, right? And in the second case, substitute j with pn, right? So the thing will be like this, so it will be reduced somehow. Now let us see here that if you remember the table, there were these symbols. If we consider these 6 symbols, that is xij minus 1, xij, xij plus 1, and for the next I counter 3 symbols, and it will be valid if xij is a state but xij minus 1 and xij plus 1 are tape symbols. This can be one choice, and there is a move m that explains how xij minus 1, ij plus 1 becomes its next, right? So this will be valid if xij is a state and its two neighboring symbols are tape symbols, and how we are moving from total this set to the next set. So this will be valid if these two are defined properly. Okay, so there's a finite number of assignments of symbols to the 6 variables that are valid. Let aij be the odd of the terms, one term for each set of 6 variables that form a valid assignment. Just see how to do it. Now first we are considering that if it moves left, right? So if we assume like this, the movement like delta q of a, q is a state and a is definitely a tape symbol, it is moving to a new state p, and c is my new tape symbol, and l means it is moving left. So it would be like what, if you look at this, and then for the first case, means for the left three symbols, that is xij minus 1, xij and xij plus 1, we will replace it with dqa, right? So d is any tape symbol, let us assume it as xij minus 1, and another tape symbol is xij plus 1, one is d, another is a, and q is my state symbol, which is xij. And if the newly generated state is pdc, so we can represent it with this value. Just see, we have replaced the position of the variable, the tape symbols with this. At one place we have written d, and for the middle one it is not a tape symbol but a state, so we have written q, and rest works similarly. Now if the movement is not left and if it has moved right, so it would be like this. The same thing in a similar way we can depict this one as well. Now aij is the odd of all the valid terms, right? All whatever the valid terms are, all if we can just or between each and every, because each and every symbols are valid, so if we just perform or between them, then it will work finally. Just see, so if we have to define my next move as a valid next move, or next move is right, so either a part for a particular variable has to work, or b part, right? Whatever a and b's expression we have mentioned so far, and at the same time it will choose either a or b at this location, and for the next move it has to choose either of a or b. So if we follow this pattern, it can be means it can be extend up to n moves. So this can be written in formally like this. Okay. Now although a and bj can be large, because the tape can be a larger tape, right, and thus the length of ni is order of p of n, and the length of n, it will be square of it, right? Now we can write n on a tape of multi-tape Turing machine in amount of time that is proportional to its length, and the amount of time is in polynomial n. So you can see that this can be done, that means it can be done using in polynomial amount of time. So here we can say that my sat is can be done in polynomial amount of time, means it can be reduced to in polynomial time reduction, right? So if you have to if we have to visit this one, that conclusion of the Cook's theorem, we have seen that we can represent it in this form. We have defined it, u, what is u, what is s, what is n, and what is f. Just go through it once. Right, now here we have seen the running time for of this algorithm on a multi-tape is order of p square n, and for a single tape it is order of n to the power 4, right? And it is satisfiable if and only if m accepts w within n number of moves. We have also seen this, and we can draw it like this. Just see, the importance of Cook's theorem is, if some NP complete problem P is in P, then P is equals to NP applies to it, right? Suppose a SAT had a deterministic Turing machine that recognized its instances in polynomial time, say this one Qn. So if we have already proved all this thing, okay, so if it has a deterministic Turing machine, since we have seen that the total conversion or the total implementation can be done in polynomial amount of time, and we followed some approach, and we can see that if we begin with a non-deterministic approach, and after that we have covered all the paths, still we have proved that this can be completed in polynomial amount of time. That's why you can say in this case p is equals to np, and that too we are saying that using a deterministic Turing machine that can be say completed in qn moves. So it can be like in every language accepted by a non-deterministic Turing machine M that accepted within polynomial time Pn would be accepted in a deterministic Turing machine polynomial time by DTM, whose operation is suggested in this figure. You can just consult the figure, and the input W to M is converted to a Boolean expression. We have converted it, and this expression is fed to the SAT tester, and whatever the tester answers about EMW, or algorithm answers about W, right? So you have seen that how we have mapped our non-deterministic approach, which was completing in polynomial amount of time, that can too be completed using a deterministic approach, where we have just used so much of Boolean expressions, but till if we follow that three points correctly, start right, if the next move is right, and if my finishing is right, so you can see that the total approach is ultimately becoming a deterministic. It is following a deterministic way, because we are choosing the right move out of n number of moves. We will choose the right path. So if we follow that fashion, so you can see my SAT can be a tester, it can be a benchmark, right? So using that tester we can test for any problem. Okay. This much for today. In the next class we will see few examples of NP complete problems from other domains, and that will be the end of this module. Thank you.